I think we're a little late because we were having such a good time outside, which is a wonderful thing to do, to see all of us here in person, you know, celebrating one of our really most cherished events in the Department of Atmospheric and Oceanic Sciences. So we are here for one of our named lectures, the Department of Atmospheric and Oceanic Sciences annual Michio Yanai Distinguished Lecture. So for those of you who I haven't had a chance to meet, my name is Miguel Garcia Garibay. I'm now the Senior Dean of the College and also the Dean of the Division of Physical Sciences. So to give you an idea, in my role of Senior Dean of the College, now I get to interact with people across the entire College of Letters and Sciences, which is actually a remarkable honor and experience. But as a member of the Department of Chemistry and Biochemistry, I'm part of the Division of Physical Sciences, and that's really where my strongest intellectual and social interactions take place. And so the Division of Physical Sciences really is in my opinion, and certainly I think there's many metrics that support that, it's a really innovative community of scientists who are dedicated to exploring the frontiers of human knowledge, right? So we have from the smallest to the largest and the most relevant ones, which is, of course, our planet and what happens where we live. We address the most pressing needs and curiosities of our universe. We educate our students to go on to contribute to the economic, social, and intellectual vitality of our society. And so that's really amazing. So in addition to atmospheric and oceanic sciences, the Division of Physical Sciences includes my own department, Chemistry and Biochemistry, Earth, Planetary, and Space Sciences, Mathematics, Physics and Astronomy, Statistics, and we're also the home of the Institute of the Environment and Sustainability. We also have a number of institutes and centers that are affiliated, and some centers actually reside and live within AOS. I don't know if everybody knew, but actually the Division of Physical Science is home to 3 of the largest graduate programs in the division. So we are incredibly proud that 7 of 8 Nobel Prize winners from the UCLA faculty are in physical sciences, including our most recent Nobel Prize laureate, Professor Andrea Ghez, who was awarded the 2020 Nobel Prize in Physics. We are also very proud that UCLA's Department of Atmospheric Sciences is top-ranked nationwide, from pioneering work on weather analysis in the 1940s to the establishment of the first climate science major among top research universities. Our department trains students to be effective science communicators and the next generation of researchers and environmental managers, and so much in between. AOS has a deep history of leading the way nationally. The department is well positioned to remain at the forefront of being a force of change as it continues to engage in research that generates data to help policymakers understand the science behind climate change, man-made and otherwise, and strives to establish ways for Bruins to be an active part of solutions for these urgent needs. This evening is named in memory of a leading pioneer in the department, Michio Yanai, a great scientist and an outstanding leader, mentor, and an expert in tropical meteorology who was a professor at UCLA from 1970 to 2010. We are honored by the Yanai family establishing this important lecture series and by their ongoing multi-generational support of AOS. First, through their mother, Yoko, whose gift established the Michio Yanai Distinguished Lecture in loving memory of her husband, and most recently, Takashi and Satoshi Yanai's philanthropy, together with their wives Patty and Joanne, to establish the Michio and Yoko Yanai Endowed Department Chair in Atmospheric Sciences. Why don't you just join me and give him a big round of applause? I mean, I think all of us know that UCLA would not be the institution it is today if we were to rely exclusively on the support from the state of California with a whopping 7% contribution to our budget, right? So it is really dedicated alumni and friends of UCLA who made possible for us to have places like this, an event like this to take place. Our lecture series would be very poor without contributions like this from the Yanai family, so we're very grateful for your support. So we're very pleased to have Takashi, Patty, Satoshi, and Joanne with us this evening. Thank you for being here and for giving UCLA an opportunity to recognize your parents' long-lasting legacy at UCLA and beyond. I would like now to invite Satoshi to make remarks on behalf of the Yanai family. Satoshi.
Thank you much. Thank you very much. As always, it's an honor to be here, and our family is grateful to UCLA and the department for fulfilling my mother's wishes and doing such an outstanding job every year in organizing this lecture series in memory of my father. Due to my father's long association with UCLA, even though I never had any formal relationship with the university, it's always felt like home. It's a genuine pleasure every year to attend this lecture series, which I always find to be enlightening and informative. And on a more personal level, I feel sure that my father could wish for no greater legacy than providing a forum to feature the work of outstanding scholars in the field that he loved, at the institution he was so proud to be associated with. As it turns out, neither my brother nor I ended up following in my father's footsteps as a scientist. But as is becoming more strikingly obvious every day, climate change, a topic of tonight's lecture, is something that we're all encountering the effects of in our professional and daily lives, no matter what we do. I'm a workers' rights attorney. In my own field, among the fastest growing concerns are the health and safety impact on workers of extreme heat or working in areas impacted by wildfire smoke. And so I'm very excited and looking forward to hear this year's speaker, Professor Randerson, and his lecture on the impact of climate change and wildfires on California's forests. But more generally, I'd like to express again my gratitude for this lecture series that always leaves me better informed about the functioning of the world we live in. And we're not even done today, but I'm already looking forward for next year. So thank you very much.
Thank you so much, Satoshi. So I would like now to invite Alex Hall to introduce our speaker. Alex is the director of the UCLA's Center for Climate Science and UCLA's Climate Wildfire Institute. He is also the interim director of UCLA Sustainable LA Grand Challenge, and of course, he's a professor of AOS. Alex.
Well, it's really a great pleasure to introduce our speaker tonight, Professor Jim Randerson. He comes to us from our sister/rival campus in Orange County, Irvine. He completed his bachelor's degree from Stanford in 1992 and his PhD in 1998. He did a postdoc at Berkeley and also at University of Alaska after that, and then he was a faculty member at Caltech, and then finally coming to Irvine in 2003. And he is the Ralph J. and Carol M. Cicerone Professor of Earth System Science at UC Irvine. His research has really been instrumental in transforming our understanding of contemporary and future changes in the global biosphere. Within this large theme, he has made significant contributions to our understanding of the coupling of the water cycle and the carbon cycle. He has also studied how climate and carbon cycle feedbacks are likely to evolve in the future, especially those related to vegetation and the land surface. And as if that weren't enough, he's also widely known as a wildfire expert, studying how patterns of fire are changing in response to climate change and land use change in places as diverse as Alaska, Brazil, and California, which we'll hear about tonight. He's been prolific and influential in these areas and is highly decorated for his work. He won the McElwain Medal from the American Geophysical Union in 2005 and the Sellers Global Environmental Change Award in 2017. He is a fellow of the American Geophysical Union and a member of the National Academy of Sciences. Jim is so humble. When I look at him citing these honors, it looks like I'm roasting him. So compliments are like roast to Jim. A hallmark of his methods in this research is intensive and really creative use of observations and models and theory. And I think in this basic respect, the namesake of this lecture, Professor Michio Yanai, would find in Jim Randerson a kindred spirit. His work understanding the changing biosphere in the Anthropocene, has now led him to ponder inevitable questions relating to sustainable management of ecosystems and the design of optimal solutions for climate mitigation. I'm sure tonight he'll be helping us to make sense of these weighty questions in a context that's very close to home for us. So please join me in giving a warm UCLA welcome to Professor Jim Randerson.
It's really nice to meet the Yanai family before, and it's really an honor for me to give this lecture. I've really enjoyed the last 2 days in the Department of Atmosphere and Ocean Sciences. Just loved meeting the students and the faculty, and look forward to stronger and productive collaborations moving forward. So today I'm going to talk about climate change and wildfires. Some of this work actually started from a collaborative project with Alex Hall, and it was really nice. A project that was funded by the University of California Office of the President, using money that comes from the lab fees management of Los Alamos and Lawrence Livermore National Labs. And so really enjoyed working with Alex, and here I'll show you some of the results. So to begin, I want to just show this iconic time series from our colleague, Dave Keeling at UCSD. His son, Ralph, is continuing this work now and continuing the Scripps carbon dioxide time series. And this is potentially the most influential global change time series in the world. It's, I think, equivalent in some ways to an image of double helix for DNA for environmental scientists. We're now above 420 parts per million. And so this rise of CO2 is really the driver of the warming that we've experienced in the Western US. And patterns of warming across the globe are somewhat heterogeneous. There's been about a degree or 1.1 degrees of warming since the middle part of the 19th century. And in the United States, we've had intense warming across the West, across California, Southern California in particular. And what I'm going to really focus on in my talk tonight is what are the consequences of this warming for the ecosystems that we love, for the forests, and for wildfires, and how they're changing. And I'm going to describe how they may potentially change into the future. So I'm now borrowing a slide that I've updated from Park Williams. He's another professor at UCLA. And it shows the progression of wildfires for different ecoregions within California. And what you'll notice is that over the record for which we have relatively good satellite data, there's a pretty strong increase. Oh, let me see, something is happening with mine. There we go, okay. And so with these time series, one thing that you can see is that just in the last 5 years alone, we've had several horrific fire seasons, 2018, in 2020 and 2021. The burning has been particularly intense in Northern California and the Sierras, north of the Bay Area. In Southern California, it's been important, but moderated and has not shown the same change that we've seen in Northern California. So some of these fires, I'm going to focus today and show you some results from individual field measurements and modeling analysis of the Caldor fire and the KMP complex fire that were in the Sierra Nevada. And I'm going to describe some of the processes by which climate controls these fires. So I'm going to focus on, well, before I start, I'd like to just also show this plot that really shows this shift between the fire activity between Southern California and Northern California. So on the bottom, this is the fire. This is kind of a fraction of the total amount of fire, 100%, and it's the distribution of that fire between Southern California in the red and the Sierras and the North Coast and interior mountains. And you can just see this progression of the increase in the fraction of total fire moving into the northern part of the state, where in the past it's been usually too wet and moist to burn. And climate change has had a role in basically lifting the lid off of the vulnerability of these ecosystems. So I'm going to focus on kind of 4 stories in my presentation tonight. And I'm hoping these results are not totally intuitive and that they'll give you some new insight about the linkages between how people, climates, and ecosystems are interacting. So the first point that I'll focus on is that human-ignited fires tend to be faster out of the gate. They're more explosive. So I'll show you some evidence of how that works. Then I'm going to talk about how, I think this is counterintuitive, that fires are ignited by people, not by lightning. They actually have a sensitivity to climate, even though these are fires that are often set accidentally. Then I'm going to describe some of the smoke. We've been hit, I think especially in 2020, where it was almost surreal, the smoke coming from Northern California causing very dark periods of just, almost feeling like twilight or nighttime with this really deep transport of smoke into the upper troposphere that led to really important health effects for many people across the state. And I'm going to describe how some of the measurements we've made allow us to characterize how old that smoke is when, in terms of its radiocarbon age. And then finally, I'm going to describe how forests are changing and responding to this climate change. And I'm going to note that in Southern California, we've identified that forests are having a hard time coming back after fire. So this first step, I really enjoy using machine learning and kind of combining data analysis with climate theory and with measurements from satellite observations. And so colleagues at UC Irvine, project scientist Yang Chen, a number of us have come up with an approach. It's like an object-oriented clustering and classification process to group together raw thermal anomaly measurements that are measured by satellite and group them together into individual fire events, and then use this to track how the fires are evolving over time. So it's kind of if you think about these new programming languages like Python, object-oriented, we're creating like an object-oriented approach for studying fires, where once we know that an object of a fire exists, we can then go and grab information on the climate. We can go and grab information from big data sets of what the land surface is like. And we can do that in near real time to try to predict how the fires are going to change. And so if you were to just store all that data a priori across all of California, it would be so much data that it would be very difficult to do the calculations quickly. So this has been really fun, and let me just show you, this is what the raw data look like. This is an image coming from Suomi NPP. This was in August, and I believe this is August of 2020, and it shows, I think on August 17th, a lightning storm that ignited a bunch of fires. And the way that these satellites work from NASA is twice a day, they're traveling across the sky, and then the Earth is spinning, and then they'll come back and they'll measure the same spot on the planet 12 hours later. And so they'll measure at 1:30 in the afternoon, satellite comes back and measured it again at 1:30 in the morning. And it's just kind of like a picture from your camera, but the fires are just these little pixels of thermal anomalies, and you can't tell if you look at this, it's the red little dots, and you can't tell if that's like 100 different fires or if that's an individual fire, and it's just a pixelated image. And so what we've been really focusing on at Irvine is to try to take this information and then pull it together and put it into these clustered objects. And so here's an example from like one time step on the left, moving to another time step on the right. The older active fire thermal anomaly detections from the satellite, and so this is like the emission of radiation from the surface is detected, are shown in black, and then the new observations are shown in the brown. And then our object machine learning draws a polygon using an AlphaHo algorithm around a minimum distance polygon around this new set of points. And then it makes decisions about whether these new active fires, whether they're going to be a part of the existing fire. And so in this next time step, there was a new burst of fire activity. And so then these fires merge together. And what's really interesting is that some of the most devastating fires in California are ones that start from multiple ignitions. There'll be either multiple human or lightning. A lightning storm will travel across, for example, the Southern Sierra, and it will ignite 5 or 6 strikes. And this creates, I think, a real challenge for fire suppression and firefighters. And these events will start growing together. So let me show you an example of this. Well, here's the Bobcat fire that burned in Southern California in 2020. So you can see you can see all the active fires, and then you can see this progression. And then now that we're considering an object, you can also identify what part of the fire is actually active right at the edge. Where is it growing? And that's the yellow area. And so you can measure, do a lot of geomorphological analysis of how the object is spreading over time. So this is one example, and you can analyze what's happening within an individual fire. You can also look at how across an entire fire season for the state, how much stress is in the system. So now on the top, this shows the total amount of the area day by day. We're able to do this and apply this algorithm for both that morning, or the afternoon overpass and then the early morning overpass. So we get two types of information a day, and you can look and compare fire seasons. So this is starting at the beginning of the fire season over here and going through to the end of the fire season, and you can compare individual years. And you can see right off the bat how 2020 was a record year. And then what's, I think, really also exciting is that you can also say, well, how much of that fire front, the part that's actually burning where it's growing, is happening on a given day. And so where we think this can be really valuable is that you look, this is the day where California's fire suppression resources were stressed to the maximum. And we're working on a concept and a theory right now that actually we may have run out of people on that day. This is like 15 kilometers of actively fire burning front. And you can imagine during one of these events, you're trying to bring firefighters from all over. And I think that we as a region can run into a situation where we actually run out of resources. And once that happens, you have to kind of triage your investments in suppression, and then the fire season can even get larger. And I'm going to talk about this in another example in just a moment. So this is kind of the advantage of being able to track these fires on 12-hour increments. So here's an example now, a visualization where NASA colleagues at Goddard Space Flight Center have taken our data and used it to with the overlay in the terrain to show how the Caldor fire, which burned into South Lake Tahoe, how that fire evolved. So it started down in the southern part of the domain in the Sierra foothills, and you'll see. Did it start? Oh yeah, it's starting here. Oh, this is strange. I think there's like a delay in my my monitor. I'm hoping it will start. Let me see. Let me see if it's. Let me see. It's showing on my screen that it's going, but it's not showing on the big one. Let me just try. This is a really neat visualization. I want you guys to be able to see it. Let's see. Let me try one other thing here. Do you have a suggestion? Let me see. Let's try it. Let's go back over here one more time. All right.
Oh, it's not doing it.
Yeah, it's not doing it. That's okay. All right. Well, this is going to be a really cool visualization of the fire was going to start down here, and it was going to grow up, and it burns up to Desolation Wilderness in the upper left, and then it runs out of fuel up there because Desolation Wilderness is this really sparse, beautiful wilderness area, and it burns through very quickly in the middle through Grizzly Flats, which is a community that was devastated and destroyed by this fire. And then it gets up to southern Lake Tahoe, and then there's an immense effort of thousands of fire trucks that are putting it out as it's moving into the urban community there, and they actually stop the fire front before it gets into the South Tahoe community. And so we've made this same plot for, let me just keep advancing it, just see if anything happens. Yeah, it's not. Okay. Now it's a little stuck too. Let me just see. Oh, okay. Oh, it's going to do. Okay, here we go. All right, yay. See if I remember it correctly. And so the red are the actual thermal detections from the satellite, and then our product is the perimeter that's allowing us to make this object. You can see it burning up, and then it crosses, I think, the highway that's moving up there into the ski zone, but then it dies out in those Desolation Wilderness Mountains. And there, it's burning into Kirkwood. I think it actually damaged some of the area there. And it's burning up. And so one thing that we've identified that I think is really fascinating, and it's relating to climate change, is that these fires in the Sierra, they they like to travel up what we call, oh, is that okay? No. They like to travel up what we call shrub superhighways. The fires actually move faster in shrublands than they do in chaparral than they move in forests. So there are these canyons that kind of, a lot of the fires are ignited in the lower part of the Sierra, and they'll burn up the canyons. And the reason for this is that shrubs, they're more connected to the atmosphere. There's a greater coupling, so the winds can be faster. And also, the fuels are really dry and they're really small, and so that leads to a release of energy that can keep fueling the fire front. And so here's the progression, and so this fire is very typical for many of the Sierra fires. So they start at lower elevations, and sometimes they can actually burn over the top of the Sierra. And that happened as well for another fire that was burning at the same time, which is the Dixie fire. And so I had a question for you, which is if we've been able to then day by day look and extract the number of firefighters, number of bulldozers, and the number of tankers that are assigned to the fire to match its growth. And we're trying to look at the way that resources are being allocated. And my question is, there are 3 fires burning simultaneously during this fire. One was the KMP complex fire that destroyed, and I'll show you some evidence of this. It destroyed some of the sequoia trees in the south. The second fire was this Caldor fire that was burning the South Lake Tahoe. The third fire was the Dixie fire, an enormous fire that burned through the rural community of Greenville. And I want to ask you, you can raise your hand, which fire do you think had the most number of firefighters and bulldozers per unit of that active fire line length? So raise your hand if you think it was the KMP complex fire for the sequoias. Raise your hand if you think it was the Caldor fire in South Lake Tahoe, all right? And raise your hand if you think it was the rural poor community of Greenville that got the resources. And so we're now exploring, there's some really important environmental justice dimensions of how resources are allocated during a fire event. And it's critical to protect homes, but there are a number of decisions that are made that influence the damages that occur within ecosystems and within communities. So one of the science results that have come out of this analysis that I'm going to focus on now is the difference between human-ignited fires and lightning fires. And so this is closing out this section of my talk. It turns out that human-ignited fires, you can identify as well which fires started by people and which were ignited by lightning. Lightning is amazing. You can triangulate lightning to within a few meters or dozens of meters from the electromagnetic pulse. You can figure out where to triangulate, and if you find a fire that doesn't have any lightning, that's when they often send in the teams to identify if there's been a human source there. And so what we find is that these human-ignited fires, often they're being ignited during a heat wave, middle of summer, and so they just quickly burn up and get much larger over time compared to the lightning-started fires. Lightning-started fires can be horrific, and you can get complexes of multiple ignitions, but they tend to come with a little bit of moisture. It might rain a tiny bit, or it might be dry, but the humidity's gone up, and that slows the actual the growth of the fire. And what's interesting is that those human-triggered fires in the forested areas, they also, because they're burning faster, they're also releasing more heat, and they're burning hotter. So they actually have a higher rate of tree mortality. They kill more trees than fires that are ignited by lightning. And that's a part of this paper that was led by Stain Hansen in Nature Communication. So now I'd like to turn to another study, which is really, again, looking at the really high-resolution daily information on when fires start and then how much burned area occurs day by day using the satellite data. And it was led by Aurora Gutierrez, who's an undergraduate at UCI. And so this study was focused on the Sierra Nevada part of California. You can see in California that much of the Sierra, this is the area you see in red, those are fires that just happened in the last 20 years. So there's been a massive increase in fires in the Sierra Nevada part of California. And so what Aurora did, was really creative, was to break down, based on the day of the fire start, what the temperature was. So she extracted climate records from PRISM, and then this is the percentile distribution of temperature. So it's warmer on this side, and it's colder over here. And this line up here is for the number of fire starts. So this is the day the fire started, and this is the daily burned area. How much did the fire expand each day? And you can see, especially for this August, this is the August-September column, this is the June-July, you can see that in the last 20 years, we see a really large, there's a very strong positive relationship between daily temperature and fire activity. And it's true for both the number of fires or fire starts and the total number of burned area. And you can see how recent fires have really driven part of this trend. So she did a really nice analysis where she created these, we call them histograms, probability distribution functions. And what this shows is just what's it like, what's the temperature like in the Sierras. So in the top panel, it's the same information. It's just in the Sierra Nevada during summer, what's the distribution of temperature? And so the temperature is here along this axis, and this is just the number of days. So the normal temperature is somewhere around in the Sierras of about, I think, 16 or 18 degrees in midsummer. You can also then say, okay, well, what's the distribution of the number of fire starts? And that's what's shown on the left, or the amount of daily burned area, which is shown on the right. And if you look really carefully, what you can see is that the distribution of when fires start, that distribution has shifted a little bit. I'm putting on these blue lines to help your eye. You see how that's shifted a little bit to the right here for the PDF distribution of both the burned area and the fire number. And so it means that the fires are more sensitive to temperature. And then if you normalize this data here by the actual number of days that occur at that particular temperature increment, so you divide this one by this one, you get these very strong nonlinear relationships of the response of fire to daily temperature. And basically, daily temperature is controlling the moisture in the air. We call it vapor pressure deficit. And that is a critical determinant of how dry the fuel is. And so she then, you could fit this with an exponential relationship. It's much better than the linear one. And if you use this exponential model, the red line, you can reconstruct the middle distribution if you start with the distribution of temperatures at the top. And that was important. These modeled relationships in red are important because I'm going to show you in a moment how we've used that to project how summer temperatures in the future are likely to change fires in the Sierra Nevada. And so let me go to this next point. So on the upper left, this shows how the distribution of temperature has changed in the Sierra Nevada. You see by decade by decade. So on the left, it's June and July, and the right, it's August, September. And you see how these lines are shifting to the right. The solid, really thick red line is a little bit moving to the right, and that's basically climate warming shifting the distribution of temperature decade by decade. On the lower panel is how a climate model, the community Earth system model that has a representation of the ocean and atmospheric dynamics, building on the legacy of the UCLA Atmosphere and Ocean Sciences Department, many decades of work. And you can see that it doesn't do a perfect job, but it captures a lot of that progression over the last 4 decades. And then it also projects over the next 3 or 4 decades that we're going to get an increase in warming. So what Aurora did in her analysis is she used the nonlinear relationships, but she was careful, like once she got above the data, she just capped it. We didn't want to make some crazy assumption about that nonlinear line just going off into space, but she capped it at the high level, and then she combined it with the projections of the daily temperature variability from the climate model and developed these projections of how the number of fires and burned area will change in the future. And so I think what's really interesting about this is like a 1 degree increase in temperature on a given day is likely to increase the probability of a fire start and the amount of area burned by about 20%. So it's a nonlinear sensitivity. And by the 2040s, considering increases in summer temperature, we expect somewhere on the order of a 50% increase in burned area. And the model doesn't exactly, it's a little bit more conservative if you look at this for burned area than what's happened. So it's a kind of a conservative estimate. It matches relatively well the number of fire starts. And so these are our projections of solely considering the effects of this summer intensification that's driven by climate change. And so I'd like to make one comment here that I think is important, and it's answering the first part of my second question from my introduction, which is that, so how can it be that the number of fire starts, how can they be sensitive to climate? And one of the biggest fires in California's history, the Mendocino complex fire was started by a rancher, and the rancher was trying to drive a stake into the ground to put out a wasp's nest. And so this was a rancher who was well respected in the community. He was hitting this hammer, it sparked on this metal stake. I'm not sure exactly why you'd put a wasp's nest out with a stake, but he was trying to cap it. I think it was near his house. It caused a spark. The spark started a fire. It was so hot on that day when this happened that he first tried to put it out with blankets and with all the resources he had at his house. He immediately called 911. The local fire department came immediately to his house. And it also, the fire had spread so quickly that it had entered into the terrain, it entered into the chaparral. And it was basically unstoppable. And so it turns out that the state of California indemnified him. They didn't hold him responsible for this giant fire because he did everything the way he should have to try to manage his land. If he had tried to put out that wasp nest on a day where the temperature might have been the mean at maybe 80 degrees Fahrenheit, it wouldn't have been a problem. It's what he had done in decades before. But he chose to do this during a heat wave, and the fuels were so dry that the fire expanded away. And so this is a kind of a really fascinating, I think, dimension in fire research where you have an interaction between people and between climate. And even though the humans are initiating the action, climate is determining the sensitivity of the response. And so it's basically these fires are growing so quickly that they escape the initial control. And once they get to be the size of a couple kilometers, there's very little you can do to put out the fire once it enters into the forest areas. So, okay, and I'm going to pivot to the smoke that we breathe during the fires. Oh, well, I have one more. This is kind of the feedback. I may skip over this, but the piece that we really contributed in this study was that I think people had known that temperature really controls the way that fires spread and their behavior, but we were able to quantify this really strong sensitivity of the number of ignitions. So in Orange County now, during a heat wave, all of our open spaces are shut down. You can't go for a hike. You can't go out there, and I think it's for two reasons. So the Orange County Fire Authority does this because, one, they want to protect you. If there is a fire in an open space, it'll travel so fast that you do not want to be hiking. It'll be traveling where you could really get caught up. The second reason is any mistake a hiker makes is likely to just quickly create a very challenging situation for fire suppression. So I'm not sure what the policy is up here in LA, but I'm imagining it's similar. And this is the type of information, this sensitivity information can help us really potentially design better rules for how we make decisions regarding how heat waves are affecting and how we manage our open spaces and our managed lands in California. All right, the next step is measuring the composition of smoke. And so it's not all, fires in California are not all about climate change. There's huge implications of the history of management of the forests. There's an indigenous burning regime of cultural fire, amazing, kept the forests open, really protected the sequoia, and that these recurrent fires, they promoted oaks, they promoted, consumed the fuels, and kept it more like an open, really opened up the forest floor. But then that changed. There was a huge perturbation with the gold rush, the loss of indigenous people. Then in the early part of the 20th century, there was a big push by Smokey the Bear for suppression. So in a lot of our forests, there's a lot of buildup or debris, coarse-woody debris, of little trees, and this allows for a ladder fuel that can carry a fire from the surface where it's a low intensity. It can lift it up into the overstory, and then that's really a problem for sequoias and these really long-lived trees, but that's how you can kill a tree. If a fire is moving along the surface, it won't kill a tree like a sequoia. If it jumps into the canopy, then it's really problematic. So Audrey, another PhD student at Irvine, has been measuring smoke, and this isn't where she's measuring at the Blodgett Experimental Forest. It's run by UC Berkeley, and we also made measurements that I'm going to show you about. This is her instrument where she's collecting smoke filters. We make measurements of carbon monoxide, methane, particulate matter, PM2.5, and she takes these samples of the particulate matter back into the laboratory at UC Irvine and analyzes them for their chemical composition and their isotopic composition. And so we made measurements. We went to 3 rivers, right down where that blue dot is, which is right below this KMP complex fire that was burning. This is the same day that we were in our Airbnb. And this is the edge of the fire. And these areas here in the kind of the beige are sequoia groves. So on this day that we measured as kind of an initial campaign, the fires were moving and burning through some of the sequoia areas. And you can see the smoke is really thick. So what Audrey did is took the data back into the lab, and we have in the basement of our building a giant accelerator mass spectrometer that can measure the radiocarbon age. It's been used, for example, to date the Shroud of Turin and a lot of different artifacts, but she measured the age of the smoke. And so what she learned is that the age of the smoke was this value here. It was enriched. And basically, in the atmosphere, there's a really large spike from testing of nuclear weapons by the Americans and the Russians that peaked in the 1960s. And this radiocarbon has been leaving a tracer that is basically picked up by plants. And it's been falling off exponentially since then. But everything in the biosphere is labeled at the time that the photosynthesis occurred that pulls that carbon into the plant. And so if you measure it, if there's something is only in the biosphere, like a leaf or a needle that's falling to the ground, that might have a radiocarbon composition that reflects the atmosphere 2 or 3 years ago. And so that would be down here. But what she found, her measurements are, and they're very precise. There is an error bar there, and it's actually smaller than the dot. That it turns out that the age of the smoke that we were breathing, it was like nearly 1,000 micrograms per meter cubed. We had to stop our campaign short because there was so much smoke we were breathing. Luckily, we had air conditioning in the Airbnb, and luckily we were able to get an Airbnb in that community because it was a mandatory evacuation zone. So it was easy to find a good spot. But this 45-year-old smoke is interesting because what it means is that the fire was burning through. If you imagine trees and plants around here that are 45 years, it's stuff like that's outside. It's big coarsely debris chunks. It's big trees, not giant trees like a sequoia that lives for 1,000 years, but it's the material that can enable this jump into the canopy. And so we think this is evidence that of burning through the understory that enabled the fire intensity to basically kill some of the sequoia trees. And so unfortunately, in the last 4 years, especially with this KMP complex fire, the Castle fire, we've lost 12 to I think it's 16 or 17% of the sequoias in 3 years, right? And that's a tree that lives for 1,000 years, so it's clearly not sustainable. But this is an approach that we think, as California ramps up its prescribed fire to bring us back closer to that indigenous level of burning, we think that what will happen is we could sample the smoke downwind in the Central Valley and get an integrated estimate of the success of California's transformation of its forests. And if the prescribed burning program works, then we should see the radiocarbon ages reflect a more recent atmosphere. So anyway, that's when we're now going to compare it with the Blodgett forest. Then final part of my talk, I just want to go over these long-term trends in tree cover, and this was work that was led by John Wang, who's now an assistant professor at University of Utah. And he did some really nice work using a long-term satellite record of how mapping tree cover, and that's shown on the left, and on the right shows the loss of tree cover or the gain of tree cover in different parts of the state. And what's really striking, he also mapped out the types of disturbance. So on the left, it shows the amount of forest loss that's coming from fire or harvest or die-off, which is kind of like from the drought. On the right-hand side, it shows the year of the disturbance. And you can see how in the northern part of the state, you can see that all that red area, that shows that we've lost a tremendous amount of forest in just the last few years. And so what John has done is looked at this change in forest cover for different areas of the state. And in the north coast, in the Sierra Nevada mountains, and also to some degree in the central coast, the forests are not keeping pace with the increase in fire. So we're having a net loss of forest area. That's the green line on the top. And each of those, you'll see the green line kind of going up and then crashing from this increase in fire, this recent increase in fire. He also measured on the bottom panel the forest recovery in areas that haven't been disturbed. And so in the North Coast, Sierras, and Central Coast, in areas that aren't disturbed, the forests are coming back. So there's kind of a natural cycle of the fires causing damage, and then a recovery. It's the cycle is out of steady state because the fires are increasing, but in Southern California, you don't see that. You don't see this black line, which represents the no disturbed areas. You don't see the fires recovering. Or sorry, you don't see the forest recovering. And so what we think this is evidence for is that in Southern California, because we've had warming with the fires, it's very difficult for the trees to establish after a fire. It's very hot on the surface, and so this is a northward shift of the forest range, and we're losing the forests in Southern California. So we've lost 7% of our tree cover in the state. We've lost 13% of our forest cover in Southern California, and that we're finding as well that shrubs are replacing forests in many areas, and this may be making the fires worse. And so this is my last kind of, I have 2 more slides before I finish here. One is we've made projections using, looking at the distribution of species of what may happen into the future by 2100. And this is work led by a graduate student, Shane Caulfield, who was a part of the project that Alex led. And on the upper left panel is the distribution of forest on the left and shrublands. And the right panel on the upper left is the areas where we expect forest loss by 2100. And so you see in the lower elevation areas of the Sierra, especially in Northern California, that's where this machine learning statistical model that was trained like on the ecological niche, the climate niche of each particular plant functional type, revealed that we'd have a loss of forests. And there's a couple things I think are interesting. One is, and if you look at the right-hand side, it's how these species will change for individual species. So redwoods, which are along the coast, unfortunately, with this climate model, statistical model, it looks like at the southern edge of the range, they may be vulnerable, and we may lose some of the redwoods. It may get too warm. Another thing that I find very interesting is that you'll see that the canyon live oak, a lot of the oaks in California actually, they grow and they take over places that used to be dominated by conifers. And this work is consistent with earlier work by Rebecca Shaw from the World Wildlife Fund that suggests that there's this balance between the oaks and the conifers, and with climate warming, we may be pushing more of the areas into the oaks. Even the oaks are disappearing along the edges of the Central Valley, but they'll start expanding up into the mountain regions and into Northern California. So what do we do? My final slide is one that I want to just say, we need to get better at fire management. We need to be much more intelligent about fighting fires. And so I'm the science team lead for a new effort, an exploration by the Environmental Defense Fund to try to build a constellation of satellites that will measure fires around the clock every 20 minutes. We have a phase 1 where we're going to try to launch 3 satellites by 2024. And the goal really is to provide fire measurements. Instead of the satellite data that I showed you, which is at about 400 meter resolution, we dropped that resolution to 50 meters, so much finer imagery. And we're hoping to build a constellation that both government agencies, like the Australians, the Spanish, the Americans, around the world, we could build a consortium that supports this constellation, and then different fire agencies could support it in a way that would provide the data that would allow us, for example, to target fires and identify fires when they're just starting, especially like those lightning-triggered fires, and put them out. There are many places in the world, like in the Arctic tundra, where the fires might smolder for days. And if you could identify them when they're very small, it might allow teams to go in and put them out. And the goal there is not to put out every single fire, but to put out enough fires so that the fire regime stays the same. It doesn't change from where it's been over the last 50 years. And if we do nothing and we don't get more intelligent about measuring and monitoring fires, this trend, as I showed you, may continue. So with that, I'd like to thank you.
Great. Well, thank you so much for that marvelous lecture. And I think with that, we can open up the floor to questions. And Maybe I'll let you just take the questions.
Okay. All right. Thanks, Alex. Okay.
Stephen, kick us off.
Sure.
Oh, yes.
Yeah, thank you so much, Professor, for your talk. I had a question about your work's implications for future projections of wildfires. So, in your talk, you identified a really robust connection between future temperature changes,
Yes.
human-induced temperature changes,
Yes.
and wildfire
Yes.
burned area. But I'm wondering about lightning as well.
Yes.
Do you think there is a sensitivity to lightning potential increases
Yes.
or decreases in
Yes.
fire projections?
Yeah, that's a great question. Lightning is also sensitive to climate change. And in the tropics, it might go down because you need to get ice particles that are moving past each other to create friction to get the electrical charge separation. But in temperate areas, there's been really nice work led by David Romps at UC Berkeley that suggests we'll have large increases in lightning. And we just published a paper that suggests that in the Arctic tundra, it may actually go up by several fold by 2100. And that there's now evidence that they for the first time, they've seen lightning strikes in the Arctic Ocean. There was a lightning strike near the North Pole, which is really unprecedented. So there are these trends in lightning. It's really frustrating as a scientist to work with the lightning data because the lightning data is made by people who are trying to track where the lightning strikes for building damages and for fire. So they keep upgrading their network. So it's very difficult to get good data on the trend because the network keeps getting more and more efficient and they keep detecting more and more lightning strikes. So so I'm like, we want a scientific network that's like stable over time. But there's very good theory that lightning strikes will increase. And one thing that I've thought about that hasn't been worked on as well, that's really, I think, really an interesting direction with that is that for California, what if the lightning is happening, if the storms have a change in their elevation, could it be that you would get more dry lightning? If the water particles are dropping from these convective storms, maybe fewer of them will get to the surface. So the fraction of dry lightning could go up if you have a warmer surface. And so that's something I think that hasn't really been explored and it'd be really fun to think about. So it's a good point. Like, and anecdotally, when I grew up in San Diego, like we never, the weather service, like we never had summer lightning, like when I was growing up in San Diego. And then on the coast. And now, like we lost people, unfortunately, off Santa Monica. There were people who were caught on the beach and they recently were struck by lightning. And so now the weather service alerts people to, they alert the lifeguards to get people off the beach when there's a lightning storm coming across. And I feel like, personally, it's like more monsoonal now than it was when I was growing up. I don't know if other people have felt that. Like in late summer, I felt like we sometimes get really humid periods that I just don't remember. No.
Other questions?
How about so in terms of human-made fire starts correlated with hotter days, and the example you gave is just someone being a little stupid, right?
Yes. Well,
so is it because you have the same level of stupidity across all days, but other, or has the level of stupidity on hot days is that increasing too?
Well, I mean, I think really the way to frame that is that I don't know, Alex, if you're involved with this, but there are efforts underway to start potentially creating a more sophisticated heat wave warning system for California. Some heat waves are not the same as other heat waves. And what this research suggests is that there's a more intense heat wave is going to really non-linearly increase your fire risk. So we have to get more proactive about using that heat wave information to try to warn people about their either hiking or even on a ranch, how they're using the land. And so that, I mean, there's a lot of human health risks. There's even discussion of naming heat waves, the way that hurricanes are named. And I mean, there was one last summer that was really horrific for my family personally. There was a really bad one, and it was my mom living in San Diego. She lives in Point Loma, and she doesn't have air conditioning because normally Point Loma is like right on the coast. But where we got into trouble is that she really has some really nice pets, but the pets are really hard to catch in her house. And so she couldn't abandon her pets. And so we ended up having to let the pets go outside so that we could help my mom. So I mean, there's just all these situations with the heat waves, that are propagating through our society. And I think it's really, we have to be really proactive on trying to limit the fire risk during these extremes. I'm working on a paper on the heat wave fire sensitivity right now, and it's really striking. Both in California, but across the world. Yeah.
Jim and then Gavin.
Let's pursue this pipe dream of yours for a moment.
This constellation?
The fire sat.
Yeah, fire sat. Yeah.
What you're imagining is that the Environmental Defense Fund will inspire governments to do something useful. In an age in which governments are mostly not doing anything useful about climate. What's your faith in that social model?
Well, I mean, I guess, I think that, I think NASA makes beautiful fire measurements that I showed you in my talk. Those are all coming from NASA. I do think that we need to bring in a new, I think the time, things are moving so fast. I think NASA is headquartered in Washington, D.C. I don't think, if they were headquartered in Bakersfield, I think we would see a different level of motivation for NASA. They're not, and so I think that there's this really exciting, the potential for a collaboration between philanthropy, environmental groups, nonprofits, and governments is where this can really move quickly. So I'm excited about it. I was on an earlier mission with NASA, and it was going to take 8 years to get to a similar phase where we're hoping with this project to get.
That was fast.
It's fast, and so we're taking on more risk. So NASA's amazing at reducing risk, but that's at the cost of speed. Whereas like Silicon Valley is more, let's go for speed, and then, but you can actually ensure a rocket launch. So I'm learning. So you can ensure, because a rocket launch will fail at like 3 or 4 or 5% of the time, and so there are companies that will ensure that now. So then you don't have to restart and completely obliterate your startup company if it crashes on launch. Yeah.
Gavin, you want to round us up? We have time for one more question.
Thanks, Ian. It's really fascinating. So, how do you take this planned fuel treatment by the state into account in extrapolating these historical relationships?
Right. That's right. That's great question, Gavin. So the question is, did the projections that I made of wildfire include like California's 1 million acre plan to really treat the forests? And it did not. That was a simple projection with the relationship with summer temperature, assuming that the management remains as it is today. And I think the goal of that 1 million acre treatment plan is really to reduce the fire speed and intensity so that if it is burning into an area that's got a lot of high value assets like the sequoias, you could potentially put it out. Right now, if it's in tough terrain and you've got crown fires, there's just nothing you can do until you get to a point where you can basically defend it along a road or something like that. So it's a good point. I should have clarified that, Gavin. That's kind of like assuming we do nothing to really enhance the management. But that 1 million acre plan is incredibly ambitious, and it will require a scale of mobilization that the forests in California we've never tried. I mean, maybe the closest thing would be the mobilization during the Great Depression, when there was actually a project during the Great Depression. I don't know if you know this, Alex, like to build a road along the entire southern Sierra, like the whole Sierra from Northern California all the way down to the southern Sierra. They built a road to keep fires from moving up from the grasslands as a works project during the Depression up into the Sierras to protect the forests. But it's going to be something on that order of magnitude. I don't know what highway it is. Jim, you probably know what highway that is. But there's a road that actually runs parallel to the. It's kind of right between the grassland and the forest.
But it's not fully complete.
Yeah. So, yeah.
Great. All right. Well, let's thank Professor Randerson again.